No? Okay, let's look at this. This is example 11 from our section 2 worksheet. I know we haven't finished that. We have a couple more topics to discuss in section 2. So, looking at these two, we're looking at the difference between equivalent and equal sets. What is the difference between those two sets, equivalent and equal sets? Without reading, this is what you're supposed to be. This is why you're supposed to review instead of looking at your cell phones every morning.
The equal sets have the same amount of numbers, and it doesn't read the same order, but it has the same amount of numbers.
Okay, then go ahead. It does have the same amount.
And it can also be the same numbers.
It has to be the same.
Mhm.
It has to be the same number and exactly the same elements.
But it can be
Yes, the order is irrelevant, right? Equivalent sets are which ones?
where they match to like centers, like you send to another one, and it can send to the same person, but they can't.
You're getting that mixed up with
The other one.
relation.
Uh-huh.
An equivalent set is the same number, not the same type. In other words, A to 1, B to 2, C to 3. That's equivalent. They're not equal because they're different. They have the same number. They have 3 elements each, but it's not the same elements. Equal has to be equal and the same number. So look at these 3. Which ones are equivalent? Which ones are equal? Talk about each combination of these things. Let's look at sets A and B. Let's look at sets A and C, A and D, B and C, B and D, and C and D. Good morning. So what can you tell me about these two? These pairs of sets, I should say, not these two. Okay, so I'll put, because what we're looking for here, make it easier for you. This is equivalent and equal. Are sets A and B equivalent? Why not? Very good. They have different number of values, and they're different types of values. Are they equal? For the same reason. How about A and C? And equal? No, for the same reason as A and B. How about A and D? And no again. Because A has 4, everybody has 3, that means it's neither equivalent nor equal. How about B and C? Are they equivalent?
Yes.
Why? Yeah. Same number. Are they equal? Why? They're not the same. Yeah, they're not the same values. B and D. They both have 3. Are they equivalent or equal? Yes. Just because this was out of order, it doesn't matter. How about C and D? Equivalent? Yes, but they both have 3. Equal? No. Yeah. So those are the differences. Equivalent, same number, equal, same number, same elements. So also reviewing, actually, you have this on your sheet. You have these on your sheet, these questions. You could work it out in there instead of writing down your whole notes. So that way you're not wasting our time on that. Notice how the sets, the name of the set is in capital letters, the elements are lowercase. The next thing we're going to talk about are what we call empty sets, or the empty set. What do you think an empty set is? No. No. Good morning. Yes. That's exactly it. It has nothing. It's a set with nothing in it. It's an empty set. So if we had our set A. If it's an empty set, the symbol we use is that. That's the symbol for empty set. Or we can use the set notation like that. This is chapter 2, section 2. We haven't finished it since last time, so we're going to finish that first. Okay. So what's that? This is a set notation, right? Is that set notation empty? This is empty. No, so you cannot do that. If it's either going to be write that zero with a line through it or the empty brackets. You can't combine them because, but this one says the set of empty sets, which is a set in itself. Yeah, an empty set is a set of empty sets. Duh. Also, an empty set is in all sets. In other words, if I ask you to list, if I said my set is A, and I ask you to list, what method is this called? It has one of two names. The roster method or what? Nope. Just listing, right? Very good. Because here I'm listing the elements. George, if I was to list the elements of A, I would put A is in there, B is in there, C is in there, A and B are in there, A and C is in there, B and C is in there, A, B, C is in there, and also the empty sets in there. And we'll discuss what that's called in a second. But if I ask you, if I give you a set, I said, give me all the elements, all the combinations of the elements in that set, this is what you do. We have two types we talk about. A set is either finite or infinite. What's the difference? Yeah. This one you could list, there's a specific number of elements. This one has infinitely many. You can't list the elements in there. Now we're going to talk about the Venn diagram. Remember, we talked about another diagram where we didn't. What makes it a Venn diagram? Actually, they could be independent circles. Yes, there you go. A Venn diagram has to have this box around it. Yeah, because they both have those circles. This box represents the universe. The universe is what we call the elements that we're talking about. This is a universal set. The universal set is a list of all the elements in that you're dealing with. There we have set A, set B, and you list, you indicate that that's the universe. If they don't overlap, what's that called? As opposed if they do overlap. They have names. What are they? I'll give you a clue. This one starts with the letter D. This one starts with the letter C. Nope. It does start with a DI. This one. It's in there. And the other one is conjoined, or you can say the overlap or the intersecting. Now, in a Venn diagram, we have two things to consider. You have the elements in the set you're looking at. And okay, let's pretend that the universe consists of the numbers 1, 2, 3, 4, 5, 6. That's the universe. And set A consists of 2, 4, 6. So if we were going to do a Venn diagram, then we know that A is consisting of the numbers 2, 4, and 6. And what about the rest of the numbers? Where do they go? They go out in the universe, right? That's what's left out there. So whatever's left is 1, 3, 5. What is that set called? It's written as this. It's called the complement. The complement by you could define as the set of elements in the universe that are not in set A. The complement means the opposite. So if set A is 2, 4, 6, the opposite of that is 1, 2, 1, 3, 5. It's whatever's left in the universe. So we have the complement out here. Is there an example? Yes. On your sheet, let's look at example 12. We're on section 2, chapter 2, section 2, examples. A, if the universe consists of A, B, C, D, and set B is C, D, find the complement of B, the complement of the universe, and the complement of the empty set. So, what is the complement of B? Yeah, the way you do it is, since we're looking at B, go to the universe, cross out what those are, whatever's left is your complement. So the complement is AB. What is the complement of the universe? The universe is these. That's all. Remember, the universe is the only ones we're dealing with. So if we don't have these, what do we have? The empty set. The empty set is the complement to any set in the universe, I should say. So what is the complement of an empty set? Very good. The universe. Again, these are on your worksheets. Letter B. This one says, if the universe consists of all x's such that the x is an animal in the zoo. S is a set where X consists of snakes. In the zoo. What is the complement of S? Very close. You can say it that way. Yeah, you can say it that way. But you got me confused there. Yes, because X's are animals in the zoo. So this one, X is an animal in the zoo that we have to look at this. That is not a snake. You're right. You say can't say except. But yeah, you're on the right path. Okay, basically, remember, this means the opposite. So what we did here is we just put a not. That's what changes the statement from is to is not. Very good. Let's look at C. E, or no, the universe is all natural numbers. E is the set of even numbers. And O is the set of odd numbers. Find these negations or these complements. What is it? What's that called? You're right. E, the complement of E is 1, 3, 5, 7. Does that have a name? Does it have a title? It's O. So what's the complement of O? It'd be 2, 4, 6, yeah, so it's even. And they use those for even and odd. So whenever you deal with Venn diagrams, you have to include this, what the sets are looking for, and whatever's left in the universe goes inside there as well. Now we have two more important parts. The first one, we're going to talk about our subsets. What is a subset? You have that on your sheet. It is a subset A is written. Actually, B is a subset of A if every element of B is an element of A. If every element of B is an element of A, can A have more? In other words, is A a subset of B? You can't say that because it can have more, but it has at least B elements in it. So the symbol we use for subset is that. So we say B is a subset of A. If sets A and B are equal, then we can write A is a subset of B and B is a subset of A. And unfortunately, that one doesn't have an example in it. So if set A, I'm making my own example, are the numbers 1, 2, 3, 4, 5, and B are the odd numbers, then we can say that B is a subset of A. Because all of the elements in B are elements of A. Is this a true statement? Since it's not, because this has too many elements, we would do this. This stands for is not an element of. Is not a subset. So A is not a subset of B. So remember I told you the earlier example, we talked about empty sets. And if I list them out, in every set, the empty set is a subset of every set. The empty set is a subset of every set. Let's see what that means. The empty set is a subset of every set. Why? Yeah, because if I say, okay, if I ask you to list all possibilities of set A, what would they be? Element 1, element 2, element 3. Then we start pairing them off. 1, 2, 1, 3, 2, 3. Add all three of them. And none of them. So inside here, it's invisible. Nothing's in there. Now we have another type of a subset we look at called proper subsets. In mathematics, whenever we have the words if and only if, we write IFF. That whenever you see IFF, it means if and only if. So the proper subsets, as it says on your sheets, for all sets A and B, B is a proper subset of A if and only if B is a subset of A and B does not equal A. So what does that mean? B is a subset of A and B does not equal A. Whereas for subsets, we simply stated the elements of B are elements of A. They could be all of them, or they could be just one of them. What does proper subset say? It says that B is a subset of A and B does not equal A. What does it take to prove that B is not equal to A? If A had at least one extra element that B doesn't. This means that set A has at least one element that does not belong in B, or is not in B, I should have put. You have an example for that one. Yes, example 13. Set A equals 1, 2, 3, 4, 5. Set B is equal to 1, 3. And set P is equal to all the sets of X such that X is equal to 2n minus 1, where n is an element of the natural numbers. Look at the P. You have to know how to read that. What does this line here mean? How do you read that line there? Such that, so P is a set of X such that X is equal to 2n to the power n minus 1, where n, this symbol is an element of. And that n is natural numbers. What is a natural number? Counting numbers. 1, 2, 3, 4, 5, and so on. So the reason for that is whenever we're counting or we have sets, you can't have negative sets. You can't have a negative number of elements in a set. So like for here, so we said X equals 2n minus 1. This is the formula for proper subsets. Actually, to calculate the number of proper subsets. Where n is the number of elements in a set. So let's first, before we move on, that's proper subsets. We also have the number of subsets. That formula is 2 to the power n. So you see what the difference is. They both have 2 to the power n, but proper subsets have at least one less than. That's why it's minus 1. We'll come back to here in a second. Let's just see what this means. So if we had set A, it's made up of 1, 2, 3. What is my n of that set? Yeah, because we have 3 elements. So the number of proper subsets And the number of subsets so proper subsets is 2 to the power 3 minus 1. What is 2 to the power 3? Yeah. 2 to the power 3 means 2 times 2 times 2. So it's 2 times 2 is 4, times 2 is 8, minus 1 is 7. And the number of subsets is simply 2n, 2 to the power 3, which is 8. So let's look at what this says is, like I said earlier, what are all the sets we can create? If I have 1, 2, and 3, what are all the sets I can create from those three numbers? Set is just 1, is just the number 2, is just the number 3. All three of them, and the empty set. So we have 1, 2, 3, 4, 5, 6, 7, 8. That's how many subsets we have. We subtract 1, we have 7. Why do we subtract 1? Because by definition, the proper subsets stated that B cannot have the same number as A. So in other words, the only one it can't be true is we cannot have that one. So we have 1, 2, 3, 4, 5, 6, 7. A proper subset cannot have all of the elements in the set. So it's got to be different by at least one element. All right. So let's finish that up. Example 13. The questions we have here are, this is example 13. A, identify all the subsets or subset relationships that occur among these sets. So identify all the subset relationships that occur among these sets. So what does that mean? There's going to be 7 of them, and we listed them already. So set A is made up of 1, 2, 3, 4, 5. So it has 5. Set B is 1, 3. It is 2. And set P has how many? So identify all subset relationships that occur among these sets. So for 2 to the power 5 minus 1, 2 to the power 5 is what? minus 1 is 31. 2 to the power 2 . Well, yeah, 2 by 2 is 4 minus 1. Yeah, I was wondering what that. Yes, I asked you. You're correct. I was going ahead. I was finishing it. 2 to the power 2 is 4. Yes. So what kind of relationships do we have here? This one has how many? Infinitely many. Because n keeps on growing forever. But for these, the number of subsets is 31, 3, and infinity. So let's look at the subset relationships. We know that A is a subset of P. Is A a subset of B? In other words, are all of A inside B? No. Is B a subset of A? Yes. So B is a subset of A of A. Actually, yeah. Is P is too big, so P cannot be a subset of anybody. Is B a subset of P? Now, let's hold off on these because we know for only one we know for sure is this one. What are the first 3 or 4 elements of this one? So when n is 0, 1, 2, 3. Well, we can't use 0 because remember we're talking about elements of whole number or natural numbers. No, because 2 to the 0 is 1. 1 minus 1 would be this would be 0 also. So when n is 1, we have 1 set. When n is 2, we have 3. When n is 3, we have 7. So these are the elements of P. The elements of P is 1, 3, 7, 15, and so on and so forth. You see where I get these numbers from? This is my counter. This is my n. When n is 1, I plug it in there. 2 to the power 1 is 2, minus 1, 2. 2 to the power 2 is 4, minus 1. 2 to the power 3. So look at the numbers here. Are these elements of these? No, it doesn't have a 2 or a 4 or a 5. So A is not a subset of P because it has elements that P doesn't. B is a subset of A, 1 and 3. B is a subset of P, and those are the only ones we have. B, identify all the proper subset relationships that occur among these sets. We just talked about that. There should no line, sorry. We're looking at proper subsets. This, yeah, proper subsets. So those are the proper subsets. Use the right symbol. What's the difference between this and that? This is proper subset. And this is a subset. What's the difference in the two definitions?
Subset, one that it can have more elements than the other one, but it can still have the same
For a
elements.
proper subset. For a proper subset, in other words, one set has to have at least one, because remember in the definition of proper subset, we cannot have this. If you go back to the proper subset, we had, where did I put that? There. In the proper subset definition, remember, B is a subset of A and B is not equal to A. That means the only thing that can't be true is I can't have all of the same elements. So this one is they have to have at least one difference. This one, because it has an equality, they can be equal. It can be equal to or less than the sets. What else do we? Well, we talked about complement sets, didn't we? Well, I think that's it for this section, isn't it? Looks good to me. Okay, so that's it. Are there any more examples on that sheet? Oh, so okay, so that does it for section 2. Let's finish up the chapter now.